All right, so hello everyone. So today we're just going to review what we kind of covered. I'll have some questions in here. Hopefully I'll get through most of them. Before we do that, I want to do some reminders and just, test things. So, test is this Thursday. Hope that's obvious. You all have the last quiz. So the forces quiz, there was one on Newton's Law that was due this last Saturday. There's another forces quiz that is technically due this Saturday. I highly recommend you do it before the test, because remember, the purpose of these quizzes, they're not homework. They're not just like a grade for the sake of a grade. The purpose of these quizzes is to give you a sense of if you understand the concepts, if you understand how to do the math and understand the concepts. And so what happens is, if you decide to wait after the test to do the quiz, you might find after the test that you don't basically view it as extra practice and actually feedback on whether you understand it. You can either figure out you don't understand it on the quiz before the test and then improve before the test, or you can find out on the test that you don't understand it and do a better job on the quiz. And who cares if the quiz isn't really worth that many points compared to the test. So the quiz that is due this Saturday, you really should try a couple attempts before the test as practice, as feedback for you on whether or not you're understanding it. Delaying it, you're going to be practicing one way or the other. It's better to actually get some feedback on whether you understand it, doing some problems that you haven't seen before. Just like the test will be problems you haven't seen before. So, that's my recommendation to you all. I give till Saturday just to stay consistent with the structure up to this point. But the reality is, you should try it beforehand. Again, hopefully that all makes sense logically, why you should do that. The quiz is extra practice and feedback on whether you understand it. So, all right, so there's that. I also want to just speak to a few things about the test. I've already told you all a bunch of the details. 18 questions, multiple choice, 2 free response questions, pick one. None of the questions are tied to each other, meaning there is no questions where you will solve one question and then use that answer for another question. The reason for that is, so there's no questions with part A, B, C, D where they're all tied together, because I don't want to make it, if you miss one problem, that you miss everything after it. So there's none of that. Every single problem is independent. When it comes to the free response, no matter which free response, you pick one course. There's a part A and a part B. One part of it will be kinematics. One part will be forces. They might use the same givens, but you're not going to use the answer from part A to solve part B for the same reason. I don't want you to miss both things because of that. So they're independent, but they might use the same givens. That's the only thing they might have in common. So there's that. Test-taking strategies. So I've done my best, and we'll see how it all goes. I have done my best to make a test that has that balance of as many questions as possible, so that if you miss something, it doesn't kill your grade, but not so many questions that you run out of time. It's the balance I want to have. Less questions is not good. If I only had 10 questions and it's 80% of your multiple choice is 80% of the thing, that means if you missed one question, that would be 8%, and that sucks. And I also want to test all the things as well. So 18 questions, we'll see how that goes. But to that end, there's some strategies I want to mention to you all. One is that if there is a question that you are stuck on, skip it. As annoying and as challenging as that is, move on. Do not let one problem take away time that you could use for other problems. Put a star next to it. Put a star in your Scantron. Remember, I will have the Scantron stapled to your own test. You don't need to bring an extra one. You just need to bring a calculator, note card, pencil, ID. Use your time wisely. Each of these problems, if you know what you're doing, the maximum amount of time it should take you is 1.5 minutes up to 2 minutes. That is the max time for a single individual question. And what am I basing that on? I know what I'm doing, and I went through and I did the test, and I didn't rush through it. I wrote out stuff as if I was solving the test as if I was a student. I went through it, I solved it. It took me, again, this is not where I made the test. Of course, it shouldn't take me that long. I've been doing physics for a while. It took me about 15 minutes to do all the multiple choice problems. That does not mean it shouldn't take me that long. I know what I'm doing. I made the test. So the 15 minutes was kind of my goal, because my expectation is that you all will spend 60 of your minutes on the multiple choice and 20 minutes on the free response. So then that's 4 times as much time as I took and yada yada. Yeah.
So are the questions going to be like eerily similar to the problem sets, or are they like the original?
So they are. I've written every single one of these questions where the problem sets came from OpenStax. So these problems are going to more look in wording like the quiz problems. Quiz problems are also every problem from the quiz I made. Now, you want to practice all the things because it's all about the skills and things like that. Don't hear me say that and say, oh, I should only study the quiz problems. The quiz problems are not enough. There's not enough content in the quiz problems. I mention that to say that you're not going to expect a paragraph. So some of the problem set problems have like a lot of wording. I didn't write as much wording because that takes up too much space in the paper. It also spends more time on reading versus doing physics. So generally like a couple lines at most per problem. It'll be a mixture again of the conceptual questions and the problem set problems. So you're going to see some of that today. Some problems are going to have numbers, but you actually don't have to do any math. Again, you'll see a couple examples of that today. Some problems, yeah, are going to have numbers. You have to do stuff with numbers. So regardless, though, no question should take you more than a minute or a half to 2 minutes of writing, even if you're taking your time, if you know what you're doing. If you know what you're doing. In some questions, if you know what you're doing, I say that's the max time. There's a lot of questions that the amount of time it should take, if you know what you're doing, literally the only time it takes you is like the time to read the problem, read the answers, and like in that time you'll be able to figure out the answer. Those are the conceptual ones that don't require any math and things like that. So there's a mixture. There's problems, and they scale and so on the problem sets, if we ranked the problems in the problem sets on a scale of 1 to 10, where there's some problems that are like the most difficult in the problem sets, that would be a 10, and there's some problems in the problem set that are the easiest, and those are a 1. On the test, the ceiling will be lower. So meaning, I'm not going to have problems on the test that are difficulty 10. Maybe around like 8, a 7 or an 8 in terms of difficulty compared to the problem sets. The logic being, I'd rather give you harder problems to prepare and have the test be easier than that, because the alternative is having the test be harder than the practice, and no one wants that. So, that's the logic there. Also, I don't have, and again, also I'm not going to give you any problems where the math takes a large amount of time. Most of your time on every problem should be setting up the problem. The math should be very quick. At most, 20 to 30% of your time solving the problem. And that's true of the free response as well. The setup is what I want you spending the time on. Plugging it into your calculator and solving should be a quick process. It does not mean there won't be quadratic formula and things like that. Like there could be 1 or 2 or stuff like that. But it does mean like you're not going to be doing some crazy system of equations and doing a bunch of crazy algebra and stuff like that. So, okay, so that's just details of the test. Yeah, testing and strategies. Don't get too hung up on one question. Skip a question if you need to. It's worth it. The other thing is do everything you can to check your work. Again, I know time is a little tight. It's one of those tricky things where I need to give enough, but also try to give some time to check your work. The checking your work, it might be a little tight on time, but if you have the time to do it, do so. That is an important thing to do because I can almost guarantee you if you check your work, you'll find a mistake. Why? Because you're a human being and you're making a lot of decisions, and the more decisions you have to make, the more likely it is you're going to make a mistake. That's, if you've ever had to pack to go somewhere, I always forget something. Like, always. We generally don't, even if I double check, I still might miss something. But I'm less likely to if I double check it or I have a list or whatever. If you have the time, it's a challenging thing to do because your brain's going to be tired after doing a bunch of it. Like, yes, your brain's going to get used, it's going to be tiring, all that kind of jazz. The MCAT's going to be worse. If y'all think, like, if y'all have to do the MCAT, that's, I think, I've heard 6 or 7 hour test. Yeah, this doesn't even hold a candle to that. So learning mental, and the jobs you all are going into are stressful fields. So anyhow, there is some arguments to be made about being able to perform under stress because medical field is a stress. You're in a hospital, it seems stressful at least. Anyhow, that's not my goal, is to make this a stressful environment. But it is a skill you all have to learn. So, where was I going with that though? I went on a tangent, lost my train of thought. Anyway, go through it, make sure you do the best you can. Double check your work if you have the time so that you can catch the mistakes. The more you can do to catch your mistakes, the better. I learned as a physics major when I got to my upper level undergraduate courses that when I checked my work, I almost always spot a mistake. Checking your work doesn't mean resolving every single problem. That doesn't mean that. It means go through and check, does my answer make sense? Like actually thinking about, does that seem reasonable? Given all the whatever things, there's many ways to kind of do that. The other one is if you did some algebra, take your answer and plug it back into the equation and see if it actually works. Like you have, one of the answers can be right. If you all set up an equation, you do some algebra, if you plug it back in, it should work. Like that's a good thing to do. It doesn't take that much time. I think that's basically it. I'll start. So next class, my goal is to start handing out the tests even like a minute or two, like a minute. Ideally, I could start handing them out like a minute before the test actually begins. It generally takes me 2 minutes to get tests to everyone. It's very, very quick. So should be pretty quick with that, but I'll try to start a little bit ahead of time. If you arrived right on time, that's fine. I'll just hand you the test. If you arrive a few minutes late, that's fine. I'll hand you the test. Just know that if you arrive later, that's time you don't get back. If some emergency arises, just notify me and we'll figure something out. An emergency is anything that kind of falls outside of your control. And then more uplifting things I want to encourage you all on. Remember that this test, so it's going to sound obvious when it's said, but it doesn't feel this way. This test does not evaluate your value as a human being. It is not measuring your value. Not doing that. Good luck designing a test that does that. Doesn't exist because you all have value, so that's just a given. This test is evaluating whether you understand kinematics and forces, and that's it. That is literally all this test is determining. Do you understand kinematics and forces and, thinking like a physicist? And if you do poorly on the test, what does that say? You might not understand kinematics and forces and thinking like a physicist. That's all it says. That is ultimately what I am assessing. So, going into it, hopefully that gives you a bit of peace of it's not a personal affront if you do poorly on it. It just says you don't understand some physics. And no one's going to think poorly of you if you don't understand physics. Most people don't understand physics. That's life. Another thing I want to mention is the purpose I do these note cards is to reduce test anxiety. Put anything on here that you think will make your life easier and that will, things that you wish you had, the whole purpose of this is if there's things you're going to think you're going to forget, put it on here. If there's problems, you're like, man, this is a really tricky problem. What if he puts it? Put it on here. Anything that you're afraid of, not knowing, put it on the note card. The note card ultimately can't really save you if you don't know the physics, which is why I don't the reason this exists, though, is just to reduce anxiety so that you don't have to be afraid of forgetting things. It'll be on there. You can look at it. It's kind of like a safety net for specific ideas. It can't do the work for you. A trapeze person, a person walking across the wire, the safety net doesn't teach you how to walk across the wire. But if you don't know what you're doing, at least maybe it can catch you and prevent if you mess up a mistake somewhere or forget something, whatever. So that's why it exists. Put anything and everything on it. Doesn't matter to me. But yeah, the goal is that the dream is that you don't even have to look at it. Just like the safety net, the goal is you don't need the safety net. But it's there if you do. Okay, any last questions, comments? Yeah.
Is the kinematics and the forces of RQ weighted the same?
Yeah, so there's 2 free response. Each have a part A and a part B. One of the parts is kinematics, one of the parts is forces. No matter which free response problem you pick.
They're both 10% though?
Yep.
Okay.
Yeah, they're both, part A is worth 10 points, part B is worth 10 points. Yeah, 50-50. So, no matter which one you pick, you're going to get a kinematics problem, you're going to get a forces problem. All right. Reminder, I still have office hours on Wednesday and Thursday. My office hours today were packed, which was great. It was a lot of fun for me. That's not sarcasm. It is more fun when I have people in there. Especially for the test stuff, because people tend to know a lot more before a test. So it's fun to kind of work with people in that case. So anywho, that still exists. If you try to come by, it might be really full. Just remember there's other things, take advantage of them, all that jazz. All right, so I'm going to go ahead and start going through this. These PowerPoints are already uploaded. In fact, this one, so this is the updated one from when I taught this morning. Y'all will find if I the PowerPoint I'm using looks different. That's because this morning when I teach it, I modify things. So this one's already posted with all the answers in it, but we'll go through it together, and at the end of class, I'll post the ones that I use for you. There's going to be slides where basically each week we did something, and so I'll have a quick summary, and then we'll do some practice problems on it, then a summary, just go through that structure. So first week was vectors and units. Vectors, it's an arrow. And our bread and butter skill that I really, really, really hope you're good at this point is if I give you an angle and a value, you immediately know to break it into components because that's just how these problems work. So, there's a vector, some vector A, and if I gave you some angle, we draw a right triangle with arrows on it, and you find the x component and you find the y component. My dream is that you understand why we do this. That'd be wonderful if you understand the reasons why. But even if not that, at least if you can do it, that makes me happy. The dream is that you understand that the x component is just saying literally how much does this arrow point to the right. That's all the x component represents. You can almost think of it like if someone's shining a flashlight from above, it shows you how much it points to the right. It's like a shadow of it in the x direction. And then the y component is how much it points up. If you shined a flashlight from the other side, it would show you how much it pointed up, down. That's all we're finding when we're breaking it. How much does it point left, right? How much does it point up, down? Don't forget your positives and negatives. Base units, we started talking about those. Mass was kilograms. Displacement position was meters. Acceleration was meters per second squared. Time was second. Velocity was meters per second. If you see anything that's not kilograms, convert it. If you see anything that's not meters, convert it. If you see anything that's not seconds, convert it. We've had so many problems with that so many example problems with that hopefully that's a really natural thing for you. So yeah, vectors, these show up in all the problems. So I'm telling you all, like, half the test is kinematics, half the test is forces. There is like a handful of problems with vectors, but you're doing those in kinematics and forces anyway. So if you're doing those problems, you're practicing those things. But yeah, we'll just do a couple of practice problems. Here's some vectors, A, B, C, D. I drew them this morning. Add them up. What is the direction if you add up A plus B plus C plus D? What is the direction of that total vector R, whatever you want to call it? And I'll warn you all, I might be moving a little quick today because I'm basically trying to get through 5 weeks of review in an hour and 20 minutes. But again, all of this will be uploaded. So if you're like trying to write down the problem and I move on, just know that will be uploaded with all the wording and all that jazz. And you can even download the PowerPoint now with all the wording and all that if you'd like it as well. So apologize for the expediency of it all, but it's just almost a necessity to get through all the review. If you all want a video with more time given, the studio class, I have 2 hours and 50 minutes and I go through the same stuff. And so there's a lot more pauses because I have literally twice the amount of time. All right. So how do you do this? You draw the arrows, tip the tail. So there's A, there's B. You don't need to be perfect with these. We're looking for like kind of a good enough. I'm not going to be mean if I give a problem like this and have two answers that are really similar. So something like this, I think my C is a little bit long, but whatever, it gets the idea across. It's something like this. Small arrow that's kind of down. In this case, the right answer might have been a little bit to the right or a little bit to the left, whatever. If I had this problem on a test, I am not going to give you an answer that's like this and then another answer that's like this. Those are too close to each other. If this is a test problem, I'm going to give an answer like this, and then one that's like that, and then one that's like that. They'll be vastly different. Every possible answer on a test will be more than 10 to 20%. The closest answers will be 10 to 20%, but no like 1 to 2% thing. So you either have the right answer, / you're within 1 to 2% of it, or you're way off. That's kind of the rule. So there you go. That's how we add them. Tip the tail. You just draw a bunch of arrows. Again, I think my C wasn't, it's okay. I just remember my answer from this morning was a little bit different. All right, this one was just the same thing, so I'm going to delete that. All right. What if instead I do A minus B plus C plus D? Same exact vectors as before. A is slightly up to the left, B is straight up, C is down to the left, it's fairly long, and D is off to the right. Reminder to you all, subtracting a vector is the exact same as adding a negative. Subtraction is just adding a negative. It's the same exact thing. So just to kind of write this, well, I'll show you all. So negative b is just b, but backwards. The negative vector is the exact same vector, flipped 180 degrees. Mathematically, it's kind of cool to show. I think it's interesting. Say you had a vector e. I'm going to make up something. Say you had some vector that was 3i hat minus 2j hat. And you made that what's negative e? You literally just chuck a negative sign in front of all the numbers. It just flips all of them. Instead of pointing to the left, now it's pointing right. Instead of pointing up, it's pointing down, that kind of thing. So that's why it's flipping it mathematically. Just kind of good to see that connection. But yeah, as far as drawing this, it's the same old. So now that you know that negative b, the direction of it, we're going to draw A. Then we're going to draw B. Then we're going to draw C. And then D is going to be over here. And the end result is a vector that points all the way down. So that's A minus B plus C plus D. The reason it points so much down is that vector B previously was up. So if we just kind of jump back and forth real quick. Vector B was up, so it's canceling out some of this down. Now vector B is down, so not only is it adding to the downwards, but it's no longer canceling the downwards. So it's doing double duty. So it made it really long downwards. If you're just curious why they're so different. There you go. Adding them visually. Good skill to have. Gives you a sense of what's going to happen if you have forces and things like that. It's just a useful skill. When you all get to physics 2, vectors don't go away. In fact, you're going to start off the class with vectors. Shock and awe. Physics 2 is chock full of vectors. They don't disappear. Physics, shocking. The real world, direction matters. So it shows up all the time in physics. Because the real world, direction matters. Physics is just all that. All right. Vector A points 30 degrees above the x-axis. And vector, it has a magnitude of 5. I didn't even put units on it. This is just purely a math problem with vectors. Vector B points 70 degrees to the left of the negative y-axis and has a magnitude of 7. What is the magnitude and direction of A plus B? First step is, can you draw the picture correctly? If your picture is bad, everything will be bad. Or at least a lot of it will. All right, so vector A is 30 degrees above the positive x-axis. That's our default. If I just told you vector A pointed 30 degrees with a magnitude of 5, you can assume positive x-axis. That is the default that we measure angles with respect to, if not otherwise stated. But in this case, I already stated for you. So 30 degrees above the x-axis. So I'm going to go about 30 degrees above. And it's got a magnitude of 5. There's vector A in all its glory. Vector B points 20 degrees to the left of the negative y-axis. So Vector B, we're going to go to the negative y-axis, and we're going to go 20 degrees to the left of it, just like it says. So there's my 20 degrees with a magnitude of 7. Notice I drew both of these vectors independently of each other. That is the way, whenever you're adding vectors, that's generally a good rule of thumb. Yes, you can totally draw these vectors together and get a sense of what the final answer is going to be. So the final answer will be something that points this way. But you do not want to use this picture to actually solve the problem. This just gives you a sense of what the answer should be. But we are not going to use this to break into components. There's a problem on the problem set that I saw a lot of people had challenges with because it gave them A and then it gave them B and then it said found this one and that one threw them for a loop because it was shown together. The key to doing these vector problems, draw the vectors, break them in. They should each get their own right triangle. That's always the goal. So like, sure, this little thing down here gives us a sense, whatever our final answer should be, it should match that picture. I'm just going to chuck it down here for now. But how am I actually going to solve this? I'm going to take vector A, and I'm going to turn it into a right triangle. And whenever you do this, you better draw these sides as arrows. Is it up? Is it right? Is it left? Is it down? If you don't make that judgment call, you will mess up. So this is the y component of A. This is the x component of A. Now, in this case, AY is going to equal 5 times sine of 30. This is a good exercise. I guess it looks like I pulled that out of thin air. SOHCAHTOA, sine of the angle equals opposite over the hypotenuse. So you multiply the hypotenuse over. If you're not sure why it's 5 times sine of 30, that's a great problem for you to try. That's a great problem for you to practice and figure out the reasons why. Don't just take it as gospel and move on with your life. If you don't know why that is what it is, that's a very good thing for you to practice and to find for yourself. The x component's going to be 5 times cosine. Again, same thing. That's a great exercise for you on your own time. If you're not sure where that came from, please practice that. Same thing here. I'm going to draw an arrow for B. So this is going to be BY, and this is going to be BX. BY is going to be 7 times cosine of 20. Notice that the y component of B is cosine and the y component of A was sine. Opposite and adjacent is the judgment calls. X is not always cosine. Y is not always sine. You have to make it opposite, adjacent, SOHCAHTOA, all that good stuff. BX. Now, notice I did put these as positive for now. I'm going to decide to do the negatives later if you saw that and was curious. So for now, I'm just putting them all as positive. But later on, what I'm going to do, so when I do A plus B, so let's just call it C, because C. If I want to get CX, I'm going to do AX plus negative BX, because it's to the left. It's negative. You have to make a judgment call at some point to make it negative. You can decide when that is. Just don't do it twice. And don't skip it. So I'll calculate all these numbers. It won't take me that long, and I'll chuck them in here. So I'll get all the x and y components. So 5 times sine of 30 is 2.5. 5 times cosine of 30 is 4.33. 7 times cosine of 20 is 6.58. And the y component of B is 2.39. This just makes it so I don't have to write as much in this next step, which is really my goal. So yeah, you get 2.5 minus 2.39. So you get the x component is 0.11. Something feels off there. Yep, totally off. Put the wrong number there. Again, hopefully you all have seen me make enough mistakes to encourage you to also double check your stuff. And often the reason I make mistakes is I'm kind of going through it quickly. You'll have more time than this to solve this problem. 2.5 minus, here I'll write it out a little bit more explicitly, ax, ay minus by equals 2.5 minus 6.58 equals negative 4.08. And there's my x and y component. And because I have this ability to make more room, I shall. On the test, there will be a margin on the right side where I've purposely made space in so all the problems will be kind of, there'll be a blank kind of column on the right side so you have space to immediately do your work there. You will also have a blank sheet of paper stapled to the test. I will also have extra scratch paper. Like, you can write all over the test. Like, that is a thing. Because writing on these tests is very, very important. So the magnitude of c is going to be the magnitude cx squared plus cy squared, and that's going to equal the square root of 1.94 squared plus 4.08 squared. Yes, I know that 4.08 is negative, but the negative will go away. And I find that when you try to put that negative in your square root, you have a chance of making a mistake. So just don't write it at all. It's going to get squared and go away anyway. So why bother? All right, great. That's my magnitude. That's the magnitude. Now the direction, to figure out the direction, I'm going to draw C by itself. Every vector should get its own right triangle. Every vector should get its own right triangle. So I'm going to draw 1.94 to the right and 4.08 to the left. And oh, look, my answer here looks like the one we predicted in the beginning. So it's a nice little check. This is 4.517. We just found that. So if I solve for this angle, again, this is one I'm going to let you do on your own. This is one if you're like, where did this come from? It's a good exercise to try to figure that out. 4.0, so tangent inverse of 4.08 over 1.94, that's opposite over adjacent. Based on the triangle I drew, tangent inverse of 4.08 divided by 1.94, and that is going to spit out 64.57 degrees. And so my answer to this question is either negative 64.57 degrees or 64.57 degrees below positive x-axis. Both of those things say the exact same thing. Negative angle is with respect to the positive x-axis. That's below it. If you all see this, so this direction is a positive angle. This direction is a negative angle with respect to the positive x-axis. If I tell you I'm 3 meters away, I always have to tell you from what. When it comes to angles, if I don't say from what, we assume the positive x-axis. That is kind of the assumption. Unit circle, all that stuff. So many practice problems with this. Now, obviously this problem, it took a lot of time. Like, the math here took a lot of time, so I probably wouldn't give you a problem that started in this way. But the skills here, I could ask for pieces of this problem. Would be kind of how this would look like on a test. Or I'd maybe give the original vectors in some way that made your life a little simpler to begin with. So, just because a problem takes a bunch of math doesn't mean you should skip that problem. It just means I might only pick pieces of that problem to have you do on the exam. So, keep that in mind. All right, so again, this will all get posted. I know I'm zipping through this, but the goal is that it's a review, and so therefore you can kind of look at it after the fact. Hopefully most of it's like, yep, makes sense, that's the dream. Great, 1 week down. Week 2, what did we do? 1D kinematics. I defined a bunch of terms. This is when we got introduced to all our vocab. position, displacement, velocity, acceleration, variables that we're going to be using for the rest of this semester. Like, these variables aren't going to disappear after test 1. We're going to keep using them. Positions where you're located. Displacement is how far you are from where you started. Velocity is how fast you're going. And in which direction. It's how much your displacement changes with time. So I will put the... remember that average velocity, literally the definition of velocity is how much your position, how much your displacement changes with time. And then acceleration is how much your velocity changes with time. These are just the base definitions of these things. Acceleration is not whether you're moving. Acceleration is whether you're getting faster or slower, whether your velocity is changing. Velocity is whether your position is changing, and position is just where you are. Fun fact, pretty much the only thing that we can measure generally in the world is actually position and time, and then you kind of calculate the rest of these. So if you all in your labs, when you're using tracker, you're just measuring position and time, and then it calculates velocity and acceleration with these equations. So you can't like measure velocity per se. You can only measure position and then calculate velocity. So just like you are in these problems. And then the kinematics equations. Yay! Hopefully these look less intimidating to you. The first time I looked at them, they looked intimidating, but hopefully you become acquainted with them. They're just tools in a toolbox. You pick the one that does the job. If you have a nail, you grab a hammer. If you have a bolt, you grab a wrench. If you have the initial velocity and the acceleration and the time, and you want final velocity, you choose the right one. When we work with kinematics, you're going to use negative 9.8 for acceleration. When we work with kinematics, we're going to use the negative. When you do force problems and you're finding the force of gravity, you're going to use positive 9.8. You're going to decide the negative a different way. I've seen this as a common mistake. Yeah, kinematics, if you're in the air, A is negative 9.8 because gravity is the only thing affecting it. When you all do force problems, it is almost a guarantee that the answer to your acceleration is never 9.8. When you solve for acceleration in a problem, I don't think I gave you all a single force problem where the acceleration was 9.8. Because that just means that gravity is the only thing acting on it and it's a kinematics problem and woo. But that's a classic mistake that gets made. When people set up F equals ma, they say, oh, A equals 9.8. It's like never 9.8. And we'll see that. I just want to mention it now. All right. Various tricks to know. These tricks are so useful. I actually have a second slide on it because when I was doing it this morning, I forgot I had another slide on it. So anyway, they show up twice in this PowerPoint. You need to decide what the beginning and the end of a problem is. These kinematics problems have an initial and a final. What is my initial? What is my final? You have to decide that, and that's how you're going to set up the problem. So the example of this, the problem that I really like that a lot of people have challenges with, which is part of the reason why I like it, not because I like when you all suffer, but because it's making you all think. It's the tree problem with the branch that's 7 meters up. Yeah, I was like, you probably know this problem because a vast majority of people I've encountered with have had some challenges with it. It's not you're not doing complex math, but there's a skill in it that, it's this first skill. Do you know how to decide what the beginning and the end is? So this problem, you toss, man, I'm struggling to get that to fit in there. All right. You toss it upwards at 15 meters per second, and the question says it passes a tree branch 7 meters up, and it says how much additional time does it take to come back to the tree branch? So this problem, you first have to identify what you're even solving for. So it hits a tree branch. It doesn't hit the branch, but it passes a tree branch. It's going up, and then it keeps going, and it comes back down, and you are finding this time. You're finding the time it takes between those two places, when it passes the branch and when it gets back down to the branch. And the key to solving this problem, there's actually a couple ways. There's many ways to actually solve this problem. The one I generally recommend, we're solving this situation up here, when it passes the branch and then when it comes back to the branch. So the dream is that we can set this as our initial and we can set this as our final. But the problem is we don't know that much about when it passes the branch. So what you actually then have to do is say, it sure would be nice to know how fast it's going here. And so what you decide to do is make this the initial and this one the final. Find how fast it's going there. And then, if you find how fast it's going here, we call that like the final in that frame. And then that final turns into an initial. When you then set up, oh, now I know how fast it's going. I'm going to start here and end at the end. If you haven't gone through this problem, this is a really good problem to solve. Try it out. It tests whether or not you can picture. This problem is twofold. One, what are you going to start with? What two frames are you going to pick? Basically, you can think of doing a physics problem that you take a video, and you only take 2 frames of the video, and that's your initial and that's your final, and that's what you work with. You don't care what happens in between those 2 things. You only care about what happens in the first frame and the final frame. And this one, you're going to do that twice. You pick this first thing as one initial and final, and then you do the problem again with an initial and final. So it's it's a good test of whether you can do that. The rest of these are actually really straightforward, much easier. At the highest point, velocity is 0 in the y direction. If you toss an object, it'll have the same velocity but negative when it returns to the same height it started at. So if I toss a ball upwards at 10 meters per second, how fast is it when it comes right back to my hand? Negative 10 meters per second. If you're like, where did that come from? So that's actually really easy to prove using this equation. So this equation is one of the kinematics ones. If you return back to where you started, delta x is 0. And wow, final velocity squared equals initial velocity squared. They're the same. One's negative and one's positive though. And you got to be careful of that. So we find that the final velocity equals the negative of the initial velocity. Hope like that's something that might have come up in some problems. You might have used it. If you don't know that, you can generally still solve problems. But if you do know that, it's an additional thing that can help you. When an object is in the air, the x velocity is 0, or is constant, not 0. The x velocity is constant. The acceleration in the x direction is 0. Again, hopefully that's like not a new information. Hopefully you've been using that. And because of that, you end up in the x direction. When y'all are doing kinematics problems, in the x direction, you're always using this equation. Delta x equals velocity times time. And that's not a new equation. Like, that's not like a new one. You can put it on your formula sheet if you want, but you might run into some, you can only use it when the acceleration is 0. And so this literally just comes from the kinematics equation. If I write the kinematics equation in the x direction, oh, my acceleration is 0. That term's gone. So I get that x of t equals x naught plus v naught xt. If you just rearrange that, they're the exact same thing. So it's not a new equation. It's just a kinematics equation simplified. And in general, you should only use simplified kinematics equations if you know when you can do those. They're dangerous to use if you don't know when they're used. So it's good just to start with the kinematics equation and derive it every time. Unless you get, again, you know why you can use this. All right, so there's 1D kinematics. Here's an example problem. I toss an apple straight up with a velocity of 5 meters per second. What is its acceleration on the way up? There's no math here. So the key to this problem, sure, I gave you numbers. I could have even made it worse. I could have said I toss it with a velocity of 5 meters per second. It reaches this height. It takes this much time. It comes back down. Like, I could have given you all the numbers. Who cares? It's in the... Now, we're going to assume there's no air resistance. Assume no air resistance unless stated otherwise is a good assumption. Assume no friction unless stated otherwise. This is one of those examples where, sure, there's numbers. I'm not going to use them. And this is something... So unfortunately in this class, I often give you just the information you need and not any extras. I should probably have more problems actually where I give you more than you need. And you're like, why would you do that? That's so mean. Because that's the real world. The real world is a situation where they don't give you exactly what you need to figure out something. You're going to have access, so as doctors, nurses, whatever you might do in the medical field, you have lots of measurements, blood pressure, other things. I don't know, like you all know the measurements that they take. And you got to decide what's actually useful. You have tons of stuff, and you might actually decide, I don't have enough, so I need to run more tests. That's why they have people run through some more tests, because they say, I don't have enough given information to make a judgment call. It's not going to be as nice as these physics problems where I give you just a very limited set of information and say, you definitely have enough in this problem to solve it. The real world's much nastier where you might not even have enough and you have to determine what else you need and then actually find it and go from there. So, yeah, probably try to start doing more of that. I don't know. I'll have to think about it. But up to this point, yeah, you'll see some of that in the test where I give you more than you need. That's okay. It's not the worst thing in the world. It's nice when you have more than you need. All right. 2D kinematics is just 1D kinematics twice. X and Y are independent of each other. Time is the only variable that carries across it. 95% of problems, you need to find time. And you find time in the dimension where you have the initial and the final positions. If you've done 2D kinematics problems, you probably realize that at this point, every single time, when do you use Y for time? When you know the initial height and the final height. The initial position in the Y and the final position in the Y. When do you use X as the time to find the time? When you know the initial X position and the final X position. I travel a certain distance and I hit a wall. How long does it take? Same old equations. Repeats of what I already said before. Velocity in the X is constant. Velocity in the Y is not. Direction matters. Up is positive, down is negative. If you all use this equation, the VF squared equals V naught squared plus 2A delta X. If you haven't already run into this, it should have showed up in one of your problems. Remember, when you square root the other side, there's two possible solutions, plus or minus. The math won't tell you which to pick. You got to make a judgment call. At the end, is it moving up or down? That's how you decide whether it's positive or negative. The math will not tell you which one it is, at least not this equation. There is other equations that can tell you. When you all do a square root of something, two possible solutions emerge. Just like when you all do the quadratic formula, two possible solutions emerge. And you got to make a judgment call on which one's reasonable. All right. Okay, so I throw an object with a velocity of 10 meters per second at an angle of 10 degrees. The object starts at a height of 1.3 meters. If it hits a wall 3 meters away, what will be its height when it hits the wall? The answer's there, so depending on how quick. You probably won't. Again, this morning, actually, I was able to give people time to work on it. Your all's class is too short. I mean, I only have 30 minutes left. So for now, look at it, think about it. Can you visualize the problem? Can you think of how you would go about solving this? And then I'm going to start solving it. All right, so, someone's throwing something with a velocity of 10 meters per second. That's an initial velocity. It has an angle. That is immediately a flag that you got to break it into X and Y components. So I'm just going to do it now. My V initial Y is going to be 10 times sine of 10. It's a little unfortunate that they're the same number, but whatever. The hypotenuse times cosine of the angle. The X component is going to be that. Sure, I'll figure out those numbers so I don't have to write as much later on. My Y component is 1.74. And my X component is 9.84. Those numbers make sense. It's pretty darn flat. The X component should be bigger. You can see that from our triangle. The left-right is bigger than the up-down. Makes sense. Okay, it travels. It hits a wall. So it's starting at some initial height of 1.3 meters. It is going to travel a distance, and I'm actually going to do it differently. I'm going to say my X initial is 0, and therefore my X final will be 3. Delta X will be 3. Then we're going to build our beautiful table. So this table is, in my opinion, one of the best ways to solve these. It's not something I came up with. I actually generally don't use this table personally, but I have found that it is very, very useful for you all in solving these problems. And I say I don't use it not because there's anything against it. It's just not. I just write them as a big old list, and this is more organized. So you got your initial, your final, your initial velocity, your final velocity, and your acceleration, and then you make a beautiful table. So my initial x position is 0, final x position is 3, initial y is 1.3, initial final y, no clue. Initial x is 9.84, initial y is 1.74. Final x is also 9.84. Why is that? Because the acceleration is 0. The final y, no clue. And acceleration in the y is negative 9.8. Beautiful table, so nice. And then something I actually want to mention to you all. So up to this point, we've been doing our givens first, and then what we're solving for second. As you get better at doing physics problems, I actually kind of advise figure out what you're solving for first. Like that is a mindset shift that'll happen at some point. The reason we do the givens and the missing is it can maybe help you identify what you're solving for. If that's a skill that's like challenging, you can see here there's literally only 2 options. But as you get more comfortable with this, the opposite, in my opinion, is actually better. What are we solving for? We are solving for the height when it hits it, the y final. If you can figure that out before writing your givens, that's, in my opinion, better. But if not, that's fine. But it helps. It helps you solving the problem if you can identify what the heck you're trying to even do in the first place. So yeah, we're solving for y final. How are we going to do that? We're going to need to find time. We always have to find time in these problems. In this case, it's the x that's going to determine when I stop. It's after I've traveled 3 meters horizontally. I know my initial and final x. So that's how we're going to make that judgment call. We're going to use the x of t equals x naught. I'm going to write out the whole thing, even though it's unnecessary. In the x direction, that term goes away. When we eventually find the time, we'll chuck that into the y equation. Plus 1/2 ayt squared. So going through the motions, my final position is 3. My initial position is 0. 9.84 times time. So my time is going to be 3 divided by 9.84. This is a small amount of time. Makes sense. It's only 3 meters away, and this person chucked this thing at about 20 miles per hour. Remember, 27 meters per second is 60 miles per hour. So yeah, it doesn't take that long. It takes 0.304 seconds. Great. Now we're going to chuck that into this equation. My y final, y of t is the exact same thing as y final, is going to equal 1.3 plus 1.74 times my time, 0.304 plus 1/2. If you haven't realized this, when you plug 0.5 in your calculator, or 1/2, 0.5 is so much easier to plug in. They're the exact same number. I don't plug 1/2 in my calculator. That takes too much time. I just plug in 0.5. Fractions are generally easier to plug than decimals are easier to plug than a fraction, oftentimes. Definitely don't have enough room to shove that answer in here, so I'm just going to cheat and shrink everything. And that equals something. I don't know. I can't do that in my head. So 1.3 plus 1.74 times 0.304 plus 0.5 times negative 9.8 times 0.304 squared. And my final height is 1.376 meters. It ends up a little higher. It's actually kind of, you wouldn't actually be able to determine that very easily from this picture. So this ball actually will be a little bit higher than it started when it hits the wall. If the wall was farther away, it would continue. It might continue rising at this point. I'd actually have to check if it's on its way down yet. I don't know. So this problem, it could be still on its way up, or it could be on its way down. You don't have enough information to figure that out, nor did I ask you to figure that out. But It's interesting to mention that. Oh, when you all are doing these problems, when you're doing the free response problem, and you're doing all these steps, please box your answer. So the free response, I put the rubric. So the rubric's available. The more work you show, the easier it is for us to give you points. Because at the end of the day, the reason I'm giving you points is based on what you understand and what you know and what you're doing correctly. All of these steps are part of the points that I can give. Picture, given, missing, equations, all the skills you've been using. I will tell you all, if on the free response, and I need to put this, I might send an announcement with this. If you only have the answer, and the answer is correct, I will not give you all the points if there is no work shown. And the reason is, it is almost impossible for you all to solve, maybe some percentage of you all could solve these problems without showing any work. Maybe. What's more likely is you might have looked at someone else's paper and wrote down a number. So, to that end, because I believe that the process is what matters, you have to show something, which all of you should be doing anyway, you have to show something, and I'll also say if you show some work, but your work is incorrect and you magically end up at the right answer, that's also a bit of a red flag, because that doesn't happen. You getting the exact right answer will only happen if you do the process correctly. There's always a tiny chance that you made a bunch of mistakes and the mistakes canceled out, but the chance of that is pretty low. So anyway, I mentioned that. Show your work because it lets me give you the points that you deserve. And if you show your work and you get the right answer, you get all the points. I am not looking for every single one of these steps, but I better at least see something. So will you lose points if you don't have a picture? No. Will you lose points if you don't write every step of the math? No. I just need to see at least something. And if you show me something that looks correct and the right answer, all the points. If your final answer isn't correct, then that's when we look through your work and determine how much your work is correct and assign points accordingly. So I want to mention that. I haven't really had any problems with this. There is multiple versions of the test, so that also is a way I can determine that. But yeah, there you go. Fun problem. So good. All right. A car's velocity is given by v of t equals 3t I hat plus 2t squared j hat. What's the magnitude of the car's velocity at 2 seconds? The answer is not 14 meters per second. I'm going to give you all 20 seconds to look at this. Think about how you would solve it, and then I'm going to solve it. Because again, I'm running tight on time. All right, so the key to this is realizing that there's components here. It's vectors. So the velocity in the x is given by 3 times t. The velocity in the y is given by 2t squared. If you just put 2 seconds in here and then do the math, it's not correct because there's x and y components. So to that end, the velocity in the x will be 6 meters per second. Here, I'll just put the numbers in. At 2 seconds is 3 times 2 is 6 meters per second. The velocity in the y is going to be 2 times 2 squared equals 8 meters per second. If you want the magnitude of the velocity, you actually have to do the Pythagorean's theorem. 6 squared plus 8 squared. The answer comes out really nice. It's vectors, x and y, you got to keep them separated. The purpose of this problem is, do you remember the vector notation, i's and j's? They mean something. They're not just there, and you can pretend like they don't exist. They do mean something. So, great. Okay, leaves me 20 minutes for forces. This slide is the exact same as the slide before. I'd forgotten it was here. Now you get to see it twice. Forces. We started with Newton's laws. These are laws. These are not... These are based on observations of reality. Newton's laws are literally, this is how the world works. Whether you like it or not, it doesn't tell you why, it doesn't tell you how. It just says, if an object's in motion, or it's already moving, it's going to keep doing what it's doing until a force acts on it. An object not moving is going to stay not moving until something pushes it. An object that is already moving will keep moving until something acts on it. Observation of reality. It doesn't tell you why, it just tells you that's how it is. Newton's second law says if you push something, if you divide that, how much you push it by the mass of the object, that'll tell you how much it accelerates. F equals ma. And the third one says for every force, there's an equal and opposite. You push on the floor pushes back. The fly runs into a car, the car pushes the fly. Those forces are all identical, but the accelerations might be different. So, there's 3 problems I'm going to again kind of just jump through. This is we did one like this. Actually, we did a couple. And I think even one like this showed up in the quiz. I have 2 objects. Object A has 7 times the mass as object B. And I push it with 3 times the force. How do the accelerations compare? So this question is saying, how does A1 compare to A2? Or AA compare to AB? How does the acceleration of object A compare to the acceleration of object B? So the process for these is that we write our variables in terms of, so mass of A is 7 times the mass of B. The force of A is 3 times the force of B. We then write an expression that relates force, mass, and acceleration. We do not make this expression, it's an equation that already exists. We don't make our own equation. F equals ma. Now you want to rearrange this equation for the variable we care about. We care about acceleration. Acceleration, just rearrange it, algebra, is force over mass. So that means that the acceleration of object A is going to be the force of A over the mass of A. That means the acceleration of B is going to be the force of B over the mass of B. All you do then is you look at this A term and you swap them in. So the force of A in terms of B goes on top. The mass of A in terms of the mass of B goes on the bottom. So we swap those in. So the force is 3 times greater than the force of B. The mass of A is 7 times bigger than the mass of B. And the end result of this is that my acceleration F over M, FB over MB, that is the acceleration of B. That's why we make that swap in. So we can see here that my acceleration of A is going to be 3/7 the acceleration of B. If the acceleration of B is 7, then the acceleration of A will be 3. So this is how you do these problems. You write the expression, you plug in how they're different from each other, you pull out the numbers to the front. There's some examples of these. They're good to practice. You're going to keep seeing them in my class. It basically says, if things change, what's the end result? And we can think through if this makes sense. If I push something with more force, I get more acceleration. If I push it with 3 times the force, I get 3 times the acceleration. If I push something that has 7 times the mass, I get 1/7 the acceleration. So the end result also matches the logic. More mass, less acceleration. More force, more acceleration. And by doing this, we get a result that combines all that together. All right, so that's, one of these. A fly runs into a wall. How does the force of the fly compared on the wall compared to the force of the wall on the fly? They're the same. Newton's third law. Every force equal and opposite. This is that problem that we hated. Car, mosquito, that whole thing. Which accelerates more? The fly. Why? Fly's mass is less than wall's mass. The accelerations are different, but the forces are the same. And that was the reminder to you all. The fly and the car, same force, but the accelerations are a billion times different. Fly dies, truck doesn't care. All right, and then the last, just conceptual one. What's required to slow an object down? This one's an interesting one. Y'all tell me. I heard something. I just repeat it. I missed it. Friction, great. There's a friction force, but what if I'm pushing with a greater force? Will it slow down? No. So there's a problem on the last quiz about this where I had a car and I said draw a free body diagram, speeding up, slowing down. So just because there's friction, there's an additional thing we need to know. How does the force of friction need to compare to the force that's applied? If you want to slow down, so this is Newton's first law. An object in motion will remain in motion, object at rest will remain at rest, unless an unbalanced force acts on it. If they're the same, nothing's going to happen. One needs to be bigger. Whichever one's bigger, that's the way you're going to accelerate. You will accelerate in the direction of the biggest force, in the x direction and the y direction independently. So, and you all know this. When you're driving your car and you're going 60 miles per hour, it doesn't mean you take your foot off the gas. It means you're pushing the gas with a certain amount so that the force of friction and the air force cancel each other out and you stay at constant velocity. You take your foot off the gas, your applied force decreases and friction wins, air resistance wins. You push the gas more, the applied force gets bigger and you speed up. So, it's important the size of these arrows matters. They mean something. Vectors, the size of them tells you how big they are. And yeah, you got gravity and normal force. All right. And then we started doing problems with it. And every single problem is solved the exact same process. Draw a free body diagram with all the forces. And then sum up all the forces, break everything into components, add up all the forces in the x, set it equal to max. Add up all the forces in the y, set it equal to may, do math. Every single one of these boils down to this. There was only two types of problems that had an additional complexity, and that was the pulley and the inclined plane. And the key to those was redefining what positive and negative are. Redefining which way positive x is and positive y and all that jazz. So I'll show you all an example of that one in just a second. If you're not speeding up or slowing down, A is 0. Just because you're moving doesn't mean there's an acceleration. Again, if you all are in cruise control at 60 miles per hour, your acceleration is 0. All the forces are canceling out. You're still moving, but you're not getting faster or slower. All right, inclined planes. So these are the equations these are like kind of just to show you all this. If you have an inclined plane, and you have a box on the inclined plane, the force of gravity is down. There's my angle. We have to break the force of gravity into its x and its y component. So the FGY, FGX, this angle is this angle. So using that triangle, you can build these relationships. There's a couple problems like this. They're good to practice. Again, it's a good vector practice problem along with a force problem. But that is ultimately what ends up happening. The normal force equals the force of gravity in the y direction. So this is not good. FGX. So, and FGY, I'll just copy this. It's easier to do that. FGY is going to equal mg times cosine. That's why the normal force equals that because sum of forces equals ma, and you can go through that and see that. And the slides I had where I showed this, those are good to look at to figure out where any of this came from. If you're like, where the heck is this all coming from? It's all really nicely typed out in the slides. Yeah.
So in what case is the normal force not equal to gravity?
What a good question. I'm pushing a lot. So this is not an inclined plane, but it does have an example like that. I'm pushing a lawnmower with a force of 100 newtons at an angle of 10 degrees below the x-axis. If the mower has a mass of 20 kilograms, find the normal force acting on the mower. The normal force does not just equal the gravitational force. So we got a couple more. We have 10 minutes, so I can slow down a tiny bit here. Try to draw the free body diagram. On an inclined plane, I'll look at examples I'll give you. They will equal each other. On an inclined plane, the normal force will always equal the gravitational force into it. It's possible for me to give, I'm not going to be mean to give you one where that's not the case. But this is an example where, yeah, the normal force isn't, it's on flat ground, so I'm allowed. So you're always going to draw a free body diagram of the object that is experiencing the force that you care about. So I'm going to draw a beautiful picture of someone pushing a lawnmower. So good. All right, there it is. There's so many things you can draw a free body diagram here. You could draw a free body diagram of the person and the forces they're experiencing, or the forces of the ground due to the person, or the force on the ground due to the lawnmower, or the lawnmower. And you have to make a judgment call. Which one do I pick? Which one? What am I solving for? Where can I draw a free body diagram where that force shows up? We're finding the normal force acting on the lawnmower. We're going to pick the lawnmower. We're going to draw a free body diagram of the lawnmower. So there's my lawnmower. You all tell me. What forces are pushing/pulling that lawnmower? What's the freebie? There we go. Gravity, great. All right, what else? Is there anything else pushing/pulling this lawnmower? The applied force. Someone is pushing it. Which way are they pushing it? They are pushing it at 100 newtons at an angle of 10 degrees below the x-axis. So they are pushing it 100 newtons. Person is pushing a lawnmower, 100 newtons, with an angle of 10 degrees. Oh, look! A vector with an angle. I wonder what we're going to have to do. Let's immediately break it into components. Like, why not? You're going to have to do it eventually. Better to do it now before we forget. So this is going to be 100 times sine of 10. The x component of it's going to be 100 times cosine of 10. Again, good exercise for you all. If you're like, where do those come from? SOHCAHTOA. It's a good exercise to practice doing this. Opposite, adjacent, all that good stuff. So the y component's going to be 17.36 newtons. The x component, you don't actually need the x component for this problem, but we're going to do it anyway, just out of due diligence. If you don't know why you don't need it, then you should just find it just in case. All right. Great, did that in components. There's one more force acting on this lawnmower. If you want, there can be two more. We could have friction. I didn't say there was friction, so we can generally ignore it. But fun fact, if this problem has friction, it changes absolutely nothing about our final answer. So optional friction doesn't change anything. What's the other one? Normal force. Remember, if I leave my picture like this, it should be accelerating downwards. If these are all the forces acting on it, it should be accelerating downwards. Something better be canceling out those downward forces. Otherwise, it should be accelerating downwards. Normal force. How are we going to solve this problem? The same way we solve every single force problem. Sum of forces in the x equals max. Sum of forces in the y equals may. Build our equation. You got to build them. So in the x direction, there is only one force, and it is, if we assume there's no friction, it's just the F applied in the x equals max. Great. That'll do something. Who cares? Don't need it in this problem. In the y direction, I have a normal force that's up, so it's positive. I have a applied force that's down, so it's negative. And I have a gravitational force that's down, so it's negative. That equals may. In this case, my acceleration in the y is 0 because my lawnmower is not flying upwards into the sky, nor is it plummeting through the ground. So the acceleration in the y is 0. And so then if we rearrange this, I'm going to go ahead. I got some space over here. So normal force is going to equal my gravitational force plus. All I did was some algebra. The right side is 0. I added the other terms to the other side. Good. If you're not sure where that came from, good exercise to go through that motion. mg times FAY, which is 17.36. The mass of this lawnmower is 20. G is 9.8. And so we can see here the normal force is bigger than the force due to gravity because you're literally pushing into the ground. The normal force is bigger because you're literally, not only is gravity pushing it into the ground, you are pushing it into the ground, so the ground will push back accordingly. The ground will push back more than it would if it was just gravity. So the final answer is 213.36 newtons. Okay. So there is one more. I'm not going to even try to spend the time talking about it. The slides I posted have it. Not worked out per se, but it's a good. This problem here is it exists. It's interesting. I will not ask one this complex, but this problem has everything. It is an inclined plane problem with a pulley problem and its forces. So it's all the things. This problem basically says, here's this situation, draw a free body diagram of each object separately, and then draw it for that. So it's basically, if you can do this, if you can draw the free body diagram for each of these objects, you know what you're doing. So I'll post it with the right answers, and you can check it forwards and backwards. Remember that for pulleys. There is a pulley problem on the quiz due this Saturday where it's like what we've done, but it has friction. Make sure you all practice the quiz because, again, it's extra practice and it's going to determine whether or not you understand. It's not a perfect measure, but it's some measure of whether you understand how to do force problems. If you can do the quiz without using ChatGPT or someone else, that gives you a good indication you understand force problems. If you need additional resources, that means you should study those problems more. That's the reason quizzes exist. Problem set, all that good stuff. Office hours, help room, all the things. I'll see you all Thursday. I highly recommend arriving earlier than later. Make you less stressed about it all. See you then. Yeah. Oh yeah, if y'all want note cards, I'll leave them up here.
Sorry.